Okay, we're going to summarize from last time the different types of acids and bases. We have arrhenius acid and base. Remember that it has H plus that it can get for the acid, and OH minus for the base, and we get salt and water. These are strong acids and bases that form salt and water, or neutralization reactions, strong acid, strong base. Next is Bronsted-Lowry, and this is where a hydrogen is moving from one to the other. So for instance, HF would donate the hydrogen to the base, which was here is water, and we'd end up with a conjugate acid and a conjugate base. Remember, conjugate just means if I went backwards, this would act as a base, this would act as the acid. Lewis acid and base is when we're combining two things. So we have F minus here that has a full outer octet, and we have BF3, which has one that is not got any, one orbit that doesn't have any electrons in. So the F here donates the electrons, and we end up with a combination reaction. Okay, some acids can donate more than one proton. One proton donated is called a monoprotic acid. That would be like hydrochloric acid or hydrofluoric acid. A diprotic means I can donate two, so like H2SO4 or H2CO3. A triprotic would be three. So for instance, phosphoric acid, H3PO4. Many of our organic acids are polyprotic, means they have many acid ends that could donate hydrogens. An amphoteric compound is one that could act as a base or an acid. We've seen an example of that in water earlier on in the first video. We also need to worry about what's known as equilibrium constants. Equilibrium constants help us to know which way the reaction is headed the most. We only use aqueous or gases in a K equilibrium. Notice here it's the products on the top divided by the base, or the reactants. If they have coefficients, they become the exponents. A weak acid has a Ka less than 1. This leads to a small amount going forward. You can see that that would be a small, where this would be big, so you get a number less than 1. Bases, same thing. If for a weak base, we're going to have very few that go this way and a large amount that stays this way. The liquid, water, or solid does not is not included in a K. So we can look at different Kas or Kbs for different acids and bases and see how the increasing strength is. Increasing strength in acid, Ka increases. pH decreases, becomes closest to 0. For Kb, increasing strength of a base, Kb increases, while the H3O plus decreases, but the pH increases. Okay, so a lot of the acid-base stuff that we've learned has to do with acid rain. We have sulfates and sulfites that turn into sulfuric acid. We have nitrates and nitrites that turn into nitric and nitrous acid, and we could have sulfurous acid up here. And there's also one that everybody thinks is an acid, is carbon dioxide, but carbonic acid, which is this, quickly decomposes back into carbon dioxide and water, so it really doesn't do much. We do need to know that water self-ionizes. What does that mean? That means if I take two waters, one will be a donator, one will be an acceptor of a hydrogen. Remember, it was amphoteric, so it could act as an acid and a base. Because of that, if I do the concentration of each, I end up with 10 to the minus 7 for the hydronium ion and for the hydroxide ion. The Kw, because liquid's not in the equation, just the products here, would equal 10 to the minus 14. Now, we use some very important equations. This Kw equals 10 to the minus 14 is very important for us because we need to be able to find out the hydroxide and the hydronium ion concentration. We also have pH is what is equal to minus the log of the hydrogen concentration. Now, hopefully, in your card game that you played in class, you found these equations, so these should just be review. POH is minus the log of the concentration of hydroxide. pH plus POH equals 14, and the concentration of hydrogen, or hydroxide, is equal to 10 to the minus POH, and the concentration of hydronium is equal to 10 to the minus pH. So these are the equations that were used. This is a little chart that you have that you picked up as you came in. it's sort of a box to tell you how to work things. And I've also put behind this one on the PowerPoint the colors. Acids are usually red and bases are usually blue when we use indicators or pH strips. So that sort of helps you remember what side you're on. I like to do this upper route here. I don't often use the lower route, but you can. It's not a big deal. It's just easier for me to go back and forth because pH plus POH is 14 rather than have to use the exponents. But either one will work. And you'll need to be able to convert between hydrogen ion concentration or hydronium ion, pH, POH, and concentration of hydroxide. So, as we look at a pH scale, and you actually built this with the first home lab that you did, you built your own pH scale with things that were in the house. And hopefully you sort of got an idea, you know, really strong acid is what we use, lithium battery acid. We get up here, even this, we've got adult fish that die. And then we get a little bit higher and we get into soaps. So let's look at another one. This is probably more what you had, things that you tested. But you got an idea of what was an acid and what was based in your home. Now to calculate the pH, remember pH equals minus the log. P just means minus the log of whatever you're doing. Okay. Remember that concentration means molarity, and molarity was moles per liter. If the hydrogen concentration is 1 times 10 to the minus 10, then pH is minus the log of this, which would give us 10. Then we can easily find from that the POH, which would be 4, and the concentration of hydroxide, which would be 10 to the minus 4. See how it works? If we have something that's not as simple as just this 1 times 10 to an exponent, and we have something like this, we actually do need to plug it in our calculator. So we go minus the log, parentheses, plug that number in, close parentheses, and we get 4.74. Now you'll notice that it looks like we started with 2 significant figures and we end up with 3. The reason is whatever I started with in a concentration is only counted behind the decimal. The number in front of the decimal is not counted in your significant figure. So be careful with that. That's sort of tricky with pH. Let's do another example here. We're given a pH of 4.5, and what is the concentration of a hydronium hydroxide ion? And what is the POH? Is the solution acid, base, or neutral? So with a pH of 4.5, that's less than 7, so it's an acid. The POH, subtract that from 14, we get 9.5. Now we can easily find the hydrogen concentration by going 10 to the minus 4.5. And yes, you do need to put it through your calculator and actually get the number. So make sure you do the number, and this should have a capital M after it, and I didn't put that there, so make sure you do. And the hydroxide concentration is 10 to the minus 9.5. Plugging it through your calculator, this is what you get. And again, this should have a capital M after it, so put that in your notes. Here's another example. We're given a hydroxide concentration. We're using a square, remember, that you have. It's bright pink that has that pathway on it. So we're going to find the hydrogen concentration, pH, and POH. Easiest thing to do first is go minus the log of this, and we get the POH. Subtract it from 14, we get the pH. Go 10 to the minus pH, and we've got the concentration of hydronium ion. Remember, these need to be molarity. 6.73 is barely an acid right here, so it's almost neutral, what we would consider neutral. So here's your learning check. Put it in your notes. Make sure you grade it. Pause the video. Okay, we're starting up again. How did you do? Here's all the answers. Check your answers. If you need to, pause the video and check and go back over it. Going forward, make sure you score it out of 6, please, and circle it so I know that you did it. Acid base indicators and pH meters. We've used some pH strips, but common indicators are just sensitive to, they change color depending on how much hydrogen is present. We use an universal indicator a lot, and this is a combination of many weak acids. Remember, red acidic and blue basic, and everything in between is in between that. So we can use an indicator as a liquid, or we can have it on a pH paper. The paper is coated with the universal indicators. So that's what we used when we went home and we did the home lab. In honors, what we're going to do is we're going to do a titration. We're going to use a pH meter, and it actually measures the voltage between the 2 electrons and then converts that to pH for us. So it's really cool. We're going to actually graph a titration curve. So what is a titration? A titration is where we set a known concentration in the burette and we put an unknown in the flask or beaker, is what we're going to be using because we're going to use the stirring plates. And we put an indicator down here so we know when it ends. We're also going to have the pH meter, so you'll have both a visual and you'll have actual numbers that you can watch. You're going to turn your stirring rod on and you're going to drop by drop add your known concentration to your unknown concentration of a specific volume. You need to know the volume until it changes. So you have to know the reaction. So this is an acid with a base giving me salt and water. So this is oxalic acid and it is a weak acid. So I've got a weak acid and a strong base. To do a titration, again, you're going to fill the burette with your known concentration. Make sure the stopcock is closed or horizontal to the ground. You're going to fill it up above the 0, and then you're going to put what I call a garbage beaker down here, and you're going to empty the beaker or empty the burette until the bottom of the meniscus is right on that 0 line. Then you're going to just set that garbage beaker aside, put your beaker with a stirring rod in it with your known amount of unknown in the bottom with a little bit of indicator to help you. So this sort of goes through that. When your acid equals your base, then you're at an end of a titration. This is called neutralization. Neutralization, you end up with salt and water. Okay? So, burette, you have the known concentration. This is a stopcock. You start with it horizontal to the ground, and you're going to go drop by drop into the unknown concentration of, it depends on what you're doing. If you know the base goes up here. If you know the acid goes up here. If you don't know the acid, it goes down here. If you don't know the base, it goes down here. So whatever you don't know goes in the bottom. But you do need to know the volume of it. We're actually going to be making a curve like this. Ours might start with an acid and go up to the base, so it goes this way. Either way, you're going to have what's known as an equivalence point where it equals 7. And that is where the inflection of the curve. If we have a diprotic acid where it has 2 hydrogens, we end up with something like this. And if you go on to AP, you actually get to titrate a diprotic acid. So here's an example of a titration. If I have 21.2 milliliters of aqueous acetic acid requiring 15.5 milliliters of 0.215 molar KOH in a titration, calculate the molarity. So we take the molarity and multiply it by the volume to find the number of moles used. Make sure that you change the milliliters into liters. So you do end up with moles and not end up with moles per liters per milliliter. Okay? Then you're going to write the balanced equation. Since this is a 1-to-1, let's go back here. Since this is a 1-to-1 relationship and everything's balanced, we could use M1V1 equals M2V2. If it's not a 1-to-1, then you're going to want to convert it and then go from there, like this one. So you can convert the number of moles of KOH to acetic acid. Since this is 1-to-1, they're the same. Then you're going to take the moles and divide it by the volume that you put in. So I put 21.5 milliliters, again change it to liters, and you'll end up with a concentration of your unknown. Now again, if it's a 1-to-1 relationship, you can use M1V1 equals M2V2, which is our dilution equation. Now, problem 1, we need to standardize a solution of NaOH accurately and determine its concentration. A 35.62 milliliters of NaOH is neutralized by 25.2 milliliters of 0.0998 molar HCl by titration to an equivalent point. What is the concentration of NaOH? Take a second, see if you can figure it out. Pause the video and then start again. I'm going to have to hurry because I'm almost out of time here. Okay, so we're going to walk through it. You're doing a dilution solution. Okay, so how much do we have to add to dilute it to this? This is just an M1V1, and we've done that before. Okay, I'm going through this really fast because it's M1V1 equals M2V2. If you need to pause and look at it, do that. All right, so we're going to add 250 milliliters of water to the 50 milliliters of the 3.0 molar to make it 300 milliliters of 0.5. Just an M1V1. We've done this equation before, so I'm not too worried about it. Okay, that's a shortcut. Learning check. Take a second, see what you can do, pause it, and let's go on. Okay, I'm starting on because I want to make sure you get this. Okay, here's the answers. Learning check 3. And your turn.